Thanks, Karthik, for the introduction. You saved me some time so that you covered my introduction part and acknowledgement part, so I can say less in my talk. Okay, so very happy to be here and talk about my PhD thesis on language agents. Let's get started. So we know interacting with autonomous agents to interact with the world has been a central goal for artificial intelligence. And throughout the history, we have developed many methods and tasks. But I think in a very high level, existing methods can be categorized into two kinds. Those using like manual rule design or using intensive learning. And on a very high level, existing environments can be categorized into two kinds. Those interacting with humans are physical environment, or those game or simulation. I think this talk is about introducing a new kind of agents and a new type of environment. But before I talk about this, I want to quickly motivate why we need fundamentally new methods and tasks for autonomous agents. And those on the Zoom, like maybe you can mute. Yeah. So on the methodological side, if you think about designing rules to build agents or use imitation or reinforcement learning to build agents, either way, it takes intensive domain-specific efforts to build agents. And those agents cannot really generalize beyond their rule coverage or training distribution. Also, those methods are usually very intensive and hard to build, right? It takes experts like us to build. And even for experts like us, it's actually very hard, let alone most of the researchers outside AI or outside computer science. On the environment side, I think there has been this fundamental dilemma between scalability and practicality. So if you think about practical agents like chatbots or autonomous cars, it has been very challenging to collect interactions and rewards by interacting with humans or physical environments. That's why we often turn to more scalable game or simulation environments where we can have unlimited rewards or interactions. However, it has been proven very hard to transfer games to more practical setup, which is a problem known as sync-to-row transfer.
Excuse me, Shunyu, can you mute everybody? You can mute everybody so that you can it can be muted. You can mute everybody as a host. It's a little bit noisy for us to listen in the Zoom.
Oh, okay, like this.
Yeah, you can, as a host, you can mute everybody.
Smart idea. Yeah. Okay. So today I want to talk about my research that try to address these two fundamental challenges for building autonomous agents. So first, I want to talk about my work that created a new type of AI benchmarks based on large-scale real-world digital environments, such as the internet, code, or computer softwares. So I call those tasks digital automation, and solving those tasks will lead to tremendous practical values. But also, those real-world digital environments provide us a scalable way to collect reward, signal, and evaluation. And they prove very challenging for traditional rule-based or learning-based agents, and even for large language models. Because they require, real-world reasoning over real-world language and over open-ended actions. So those challenges motivate me to build a new type of agents that I call language agents, where the key idea is to reason to act, similar to how we humans think about the situation in our mind before taking actions. So I will show how this new type of agents combine ideas from language models and traditional agents, and they prove much more general and generalizable in the sense that it can work across various domains, and it can take one or two samples to generalize to new scenarios, and outperforming traditional agents using hundreds of thousands or millions of learning samples. So my work on digital automation and language agents have led to various follow-up methods and industrial products. But as the field grows, it often turns hard to understand what this complex field is going on as follow-up methods become more and more complex or even ad hoc. So in this last part of my talk, I want to shift from individual empirical tasks and methods to a more principled conceptual framework that tries to unify various agents and provide guiding future directions toward autonomous agents. So let's start with this first part, which I talk about benchmarking agents using digital automation. So what I mean by digital automation is essentially what we do every day on the computer, the task we are trying to solve. As a researcher, you can think of, filing reimbursement reports or writing code, debugging, running experiments, finding papers, writing reviews, arguing with a reviewer. All those things that we do on the computer, right? So if all those things can be automated, you can imagine there's tremendous practical value and everybody can graduate PhD in 3 years. But there has been little progress toward those digital agents. If you think about theory, right, it practically can do nothing. And the reason is that existing methods really struggle to reason over real-world language. Think of like a complicated paper or a piece of code. And existing methods cannot really make decisions over open-ended actions over long horizon. Think of search a query in Google or write a piece of code, right? Those decisions are extremely open-ended. But solving those challenges are not just key for building digital agents, right? So if we want physical agents like robots to succeed in the wild, to navigate in cities or human society, to plan out complex tasks, or to coordinate with humans or other agents using natural language, we also need to solve those underlying research challenges. So I want to solve those challenges, but at the time, all the benchmarks that use language looks something like this, right? So all those existing agent benchmarks, they reflect none of the challenges that I mentioned above. They feature simulation environments, small action space, synthetic tasks, and short horizon problems. So even if we solve those benchmarks, it's unknown like how that leads to solving some of the more practical challenges. While you may ask if the goal is to solve those, very hard practical digital tasks, why do we directly, benchmark on the web or on the computer or using those environments as a benchmark? It turns out the key bottleneck is evaluation. So for example, this WebGPT work from OpenAI is trying to solve a very practical task, right? Given a question, they build an agent that interacts with the browser to come up with this very long answer. So this is a very practical task that interact with large-scale digital environments. However, as you can see, the answer here is very hard to evaluate. So as a result, they have to rely on professional annotators to label, what answer is good, what answer is bad. And it turns out to be more of a demo for agent instead of a benchmark. So the point about making a benchmark based on those digital environments is not just about building large complex environments or having very, very challenging tasks. One of the key bottlenecks is how to build automatic reward functions. So this motivated web shop, and here is a demo of web shop. So the idea is you're given an instruction to buy a certain type of item, and web shop is this large-scale website environment where the agent needs to act like humans to click buttons and search queries and read real-world language and images. And it has to decide, when you want to buy the item and when you want to explore more. And if you explore, whether to search more or click more items, and if you search more, how to generate a query reformulation, and so on and so forth. So at the end of the day, an agent needs to decide on an item, click some buttons to customize the product, and at the end of the day, it needs to click this buy now button, and upon which the episode ends, and there's a reward from 0 to 1 given to the agent, indicating how many attributes in that instruction is satisfied in the chosen product. So as you can see, to build this environment, we actually scraped over 1 million real-world Amazon products and their associated real-world language and images to build this large-scale complex environment. But why out of all the possible web tasks we choose shopping? The key reason is that shopping is a very well-defined task where it's possible for us to synthesize automatic reward based on the attribute matching of instruction and product. And as you can see, solving this task is quite challenging because it not only requires understanding of language and images, but also long horizon decision making over this open-ended action space. So at the time, 2021, we tried to combine all the possible techniques that we can combine, right? So we use pre-trained image models, language models, imitation, and reinforcement learning. But even the best agent that we can build is only less than half of the human performance. So one analysis that we do at the time that's insightful is we look at what is the average length of the episode for those agents. And we found that for humans to succeed, it actually is a very long horizon task because humans, they actually search different queries, they check different products, they carefully look over all the different products and make decisions. But this kind of long horizon decision making is still very challenging for artificial agents. Another very exciting thing about WebShop is that we train agents on WebShop and then we deploy them to real-world environments like Amazon or eBay. And we find that those agents can actually exhibit similar performance. So this kind of sim-to-real transfer is very exciting, and it's very different from traditional agent tasks like robotic simulation. And here, the key driving force of the sim-to-real transfer is we're using real-world language to build a simulation environment, and that's enable a transfer to real-world environments with also similar language semantics. So since WebShop, this direction of web interaction has become very popular. There has been various methods that explore various aspects of this holistic task of web interaction, including visual understanding, language understanding, decision-making, exploration, planning, reinforcement learning, and so on and so forth. There has been better or more comprehensive benchmarks that try to benchmark more domains, and WebShop has been used as a testbed for various industrial developments. But I think beyond web interaction, WebShop creates this or inspires this new direction of using real-world digital tasks to benchmark agents. So another domain of this kind of flavor is coding. So we know that coding has been a very traditional task for natural language processing that's been studied for decades. But however, if you look at some of the most popular coding benchmarks today, like Human Eval, they usually look something like this. So it features very synthetic toy problems that can be solved within a file or a method or even a single line. And when this Human Eval was proposed, back in 2021, it was really hard. Best model can only solve 26% of the task. But within 2 years, this has become apparently too easy, and best methods can already reach 95% accuracy. So in this work of Swebench, we also have this philosophy of directly using real-world digital tasks. And here, the task input is actually a GitHub repository and the actual issue in that repository. And the output is a file diff that can be applied to the repo and resolve the task. And one thing that's good about this benchmark is that we can directly collect unit tests from real-world pull requests to serve as a scalable and feasible evaluation method. So can any of you guess what is the accuracy for the state-of-art large language models to solve this coding task? Okay. Okay, you're spoiling alert my second part, but we try to use large language model to solve that in a sequence to sequence manner, but they perform terribly. So even the best model can only solve 2% of the task. And that's kind of intuitive because if I ask you as a human to read over hundreds of thousands of lines of code and then type auto-regressively each token to solve the task, it's too hard. Fundamentally, we need a way to break down the problem into steps and use execution feedback to interact with the code and solve the task. At least that's the way human programmers solve the task. So if I want to quickly summarize this part, I think digital automation can be seen as a new frontier for benchmarking and training and evaluating autonomous agents. It has tremendous practical values, and it provides a scalable environment where there's a chance for scalable learning. However, the key bottleneck often is this problem of evaluation. So if we can figure out a way to scalably evaluate agents on those tasks and set up the task in a scalably measurable way, then it will be a great environment. And those digital automation tasks requires sequential decision making over open-ended challenge, and that has been a key research challenge that language models in a seq-to-seq manner or traditional learning agents cannot really solve. And solving this challenge requires fundamentally new type of agents. So this motivated the second part of my talk, which I'll talk about how we can use large language models as a tool to build language agents that can reason to act. So I'm sure all of you are very familiar with language models today now. But to quickly, give a recap, language models are developed to solve this very simple task to generate text, and it's doing so in a very simple way, predicting next token autoregressively. Since change in 2020, when GPT-3 showed that those models cannot just solve text generation, they can actually solve a variety of NLP tasks. If you can give them this prompt, providing task instructions and a few short examples. So since then, there has been a lot of progress in this direction of language models. So for example, follow-up research found that if you can not only specify the task instruction and the input and output, if you can also give demonstration of how to bridge the input and output with reasoning, then the language model can generalize better and solve a diversity of question answering tasks. So here, what we call reasoning in natural language processing, or at least in this context of LLMs, is this ability to derive new information, to update the internal context, and to bridge the input and output to solve the question. However, there has been some challenges for LLM reasoning. So let me give a very example question. So if you have a lot of money, you will probably ask some question like this. And if you give it to GPT-4, it will give you a wrong answer. And the reason is that, first, language models, they're trained and then they're deployed, but their knowledge is capped at their training time. So even the best language model like GPT-4, they have limited knowledge and their knowledge can be outdated. And also, language models are not very good at a lot of different stuff. For example, here you can see GPT-4 make a calculation error. So at the time, various people have tried to find limitations of LLM and reasoning and try to have piecewise solution to each of the problem, right? So you can have retrieval to solve this knowledge problem, or you can fine tune for this calculation problem. But I think in a very high level, I think a root issue for all of those problems is that a language model, they're trained to generate text. They're not really trained to act, right? So if you can have a way to make those models take actions to interact with external environments, for example, it could interact with Google to get new information and knowledge. It can interact with the calculator to patch up the calculation. It might serve as a unifying way to solve various problems. However, making language models take actions is really hard because that's not what they're trained to do. And especially if the task environment, the calculation action looks very different from their training distribution, it's very hard for language models to generate actions to solve this decision-making problem. However, like as a human, right? So we can solve various tasks even though we have very little experience. And the way we solve those tasks is with thinking our mind, right? So if you're going into a new website, you don't need to leverage existing, hundreds of thousands of examples or pattern recognition to solve the task. You can actually reason in your head, what do you need, how to solve the task in language. So combining these two sides of motivation leads to React, which is really about this new paradigm of agents that's trying to use language models to generate both reasoning traces and actions. Yeah. So I will show how this synergy of reasoning and acting leads to very simple ways to build various agents that's general across domains and generalizable meaning that it could solve various tasks using 1 or 2 examples. But before I talk about those empirical details, I want to quickly illustrate what is the fundamental conceptual difference between traditional agents and language agents. So all the traditional agents, in a high level, they're trying to solve this task of interacting with environment, where you have an action space defined by the environment. Right? So if you're a Atari game agent, your action space is up, down, left, right. It's fixed by the environment. And at each step, the task of the agent is that given the context, meaning all the observations and actions up until this moment, the agent needs to predict the action based on the context and to maximize the future reward. So I think the key essence of React is that we're augmenting the action space by thinking or reasoning. And thinking or reasoning is a very special type of action because first, the argument can be any language sequence, so it's an infinite space. But also, it doesn't really incur any external feedback from the environment. Right? So if you think anything in your mind, it doesn't really change the external environment. However, what it does for the agent is that it changes the internal context of the agent. So as you can see, if you think something in your mind and it's actually in the context of the agent, this thinking action or reasoning action can actually influence the future decision making through influencing the context. So in other words, thinking is a special action because it's not changing the external world, but it's changing the internal world. Okay, so this looks a little like complicated, but how do we actually use React in practice? It's actually something very simple. So all you need to do is you need to demonstrate an example task. And as a human, you just literally just write down what you think and how you act to solve the task, along with the environmental observations. And given this, trajectory, React trajectory as a example, you can condition on a new task. And condition on this prompt, the language model can generate a new initial thought and action. And this action can be fed into external environments to occur observation. And then thought, action, observation are appended to the context of the language model to generate the next thought, next action, so on and so forth. So obviously, you can use more than one example. And if you have many, many examples, you can even fine-tune a language model using those example React trajectories. So it's a really flexible mechanism to use language models. Or because today's language models are getting really good, you can use 0 examples. So what I'm showing here is like a 0-shot prompt to use React. So essentially, you just tell a language model, you're an agent and you want to do this task by using what type of actions. You give a description of the task and the action space and the format of the generation and the new task. And the language model can use this information to solve new tasks. So let's say how this very simple 0-shot prompt can solve this fairly hard question for NLP models. So given this prompt, state-of-art language model, in this case GPT-4, generate this thought, which is that, okay, I need to search what is the market cap of the 3 companies to understand how much it will cost to buy them. So it searched their market cap, and Google returns a noisy information, right? But reasoning is to organize the information, right? So I already have all the market cap, I just need to add them up. And then this reasoning incurs the next action, which is to use a search engine as a calculator to add those numbers up. And the search engine gives you a number, and the reasoning is incurs a way to stop the task and say, I have the answer now, and the answer is not enough. So as you can see, it's a very intuitive way to solve this very hard question answering task. And I would argue, like as humans, that's probably what we do. So to make this task slightly harder, right? So what I tried is I try to adversarially give some hard observations to force the model to try different strategies to solve the game, right? So instead of giving all the ground truth information. So here I give this adversarial observation, right? Nothing is found. There's no Google passage about those market caps. And then what's interesting is that reasoning gives this very flexible way to adjust the plan, right? So if I couldn't search for all three companies, maybe I can just search one at a time. So reasoning encourages new action to search one company at a time. But then I try to give an adversarial observation again, right? Instead of giving the market cap, I give a stock price of Apple. What's interesting is that reasoning, again, is used to readjust the plan, right? So if apparently, according to common sense, it's a stock price, not market cap, but market cap can be calculated by share price times the number of shares. So I can search instead what's the total number of shares for Apple, and a language model, the React continues to solve the game, to solve the task in this way. So I think the point here is that it's not just action that's providing reasoning with external knowledge or feedback or tools. Reasoning is also guiding the actions by making the plan, adjusting plan, tracking the task progress. So there really is this tight synergy that's benefiting both sides. So we try to benchmark React on a wide range of tasks, from question answering to fact verification to playing games to even shop online. And what we find is that React consistently outperform reasoning only or act only baseline. And we show this tight synergy of reasoning and acting. But what I'm most excited about is how it's able to solve the digital automation tasks that I proposed in the first part. So on webshop, React actually just used one example to reach a performance of 40% and outperform the best RL agent at the time that's using 100,000 training samples. And as you can see, if you remove the reasoning part from the example, then the performance degrades a lot, which shows the importance of combining reasoning and acting. And on Sweetbench, if we use this React approach to decompose the task into multiple steps and leverage execution feedback, the task performance is much better. So without using any example, a zero-shot React agent can perform more than 10% of the task, and it's on par with the server product industry. And this is very exciting. This means that we can directly deploy those agents on GitHub and actually solve real-world problems. And this is joint work with a lot of colleagues from our lab, and our paper will come out soon, hopefully. So React is proposed in 2023. It has already a lot of impact that year. So it has been the basis of literally all the follow-up methods of language agents. It has enabled a lot of interdisciplinary research, not only in AI and not only in computer science, but even outside computer science, like chemistry or creative art or mathematics. And it has enabled a lot of industry applications and startups that's trying to solve various problems using AI agents. So one of the most interesting application that I find of React is actually this application of chemical discovery, where scientists actually use React to build this digital agent that's trying to discover a new chromophore. So what they do is they give React some tools to train models or search information, and they give the agent a lot of data. And then the agent actually uses those digital tools and data to try to come up with some chromophore. What's really cool is that this reasoning and the reasoning of this React agent is actually connected to physical actions in the wet lab. So the agent is connected to the physical world and synthesize new chromophore and actually solve some new problem. So very excited about a lot of very exciting applications of AI agents, especially scientific discovery. I think even for the hardest task for humans, right, there can still be a lot of things that we can automate and accelerate. So I think it's a good time now to take a pause, because from this very simple idea of next token prediction, we have a language model that generates text, but then we scale them up and we see that it's able to solve a wide range of NLP tasks. And methods like React actually enable those models to solve more than just NLP tasks, right? You connect them to web, to code, to robotics, to web lab, you can actually solve even wider range of tasks. So I think it's good to reflect on this very incredible journey and ask, like, I think this fundamental question, right? So is this mechanism of next token prediction enough for general problem solving? Because that's what we see so far, right? By scaling up, by connecting various environments, it seems to solve more and more general tasks. So toward this fundamental question, our work tree of thought actually gave a negative answer. And we give this negative answer not through very complicated hard tasks, but we actually show that through a very simple task. This, for example, this task of given 24, where the idea is you want to combine 4 numbers to get 24, and you can give state-of-art language model like GPT-4 some examples and reasoning traces. However, it turns out GPT-4 is not really good at tasks, so the success rate is only around 4%. And if you look at the task, the reason that it's so hard for GPT-4 is that next token prediction is a linear mechanism that's trying to make token level decision from left to right and one by one. However, for some tasks like this game of 24, initial tokens can be very hard to decide because you really need to look ahead, understand, whether the first token is 10 is good or 6 is good. It's really hard to decide immediately at this token level. And once you generate some wrong tokens, you cannot backtrack. So for example, in this case, the GPT-4 generates 10 times, but then the task is already failed because no matter 10 times what, there's no way to combine the rest of the 3 numbers to get 24. So I think the takeaway from this kind of toy example is that this mechanism of autoregressive inference, the fundamental flaw is that it's not really good at deliberate reasoning and it cannot really look ahead or backtrack. So how can we solve this fundamental flaw of next token prediction? We really took inspiration from human cognition. So Daniel Kahn, in his book Thinking Slow and Fast, proposed that for human cognition, we have 2 systems, right? So we have a fast automatic system 1 that's trying to handle simple and automatic tasks, right? And we have a system 2 that's imposing control over system 1 to try to solve slower and more deliberate tasks. So if we can draw this parallel between system 1 and next token prediction, it seems that the way to fix it is that we probably also need some algorithm to impose control over that mechanism to solve more deliberate reasoning problems. And tree search seems to be a natural choice for such a control algorithm, which is also one of the oldest ideas in AI, right? Back in 1950s, we have, for example, general problem solver from Noel Simon. But you may ask, tree search has been around for decades. Why we really haven't applied them for those kind of natural language reasoning problems? And I think the reason is what I mentioned in React, because the space of thinking is combinatorial and infinite, and there's no feedback. So if you think about a classical domain of search, right, for example, chess, what you have is a small, well-defined action space. And there's a well-defined rule where you can actually simulate external feedback. So these 2 pieces actually enable you to design or learn evaluation heuristics. And then those search heuristics can enable you to solve those tasks. However, like I mentioned in the React part, right? So the space of thought or space of reasoning is totally different because first, it's combinatorial and infinite. And there is no external feedback, right? So no matter what you think, there is not a ground truth external observation in return. So these 2 features make it really hard to enumerate or evaluate thought as a type of actions. However, the key idea of the tree of thought is that language is not just infinite and combinatorial. It's actually compositional, meaning that there are semantically coherent units of text. And I want to give this, I want to use this game of 24 as an example to illustrate the point, right? So on one extreme, one way you can solve this task is you can search in a tree of tokens. So that will make it very easy to generate what's the next step, because the next step only there are 4 or 5 choices. But as I mentioned, it's extremely hard to evaluate whether this step is good or not. On the other extreme, you can think of searching in a bandit, or you can think of search in this a bandit of all the possible thoughts. The benefit is that it's extremely easy to evaluate whether a thought is good or not, right? So you can just look at whether the final number is 24 or not. But it's extremely hard to generate a good thought, because if you generate a good thought, then the task is already solved. So in this task, it seems like the right level of balance is to search in this space of intermediate equations, where you can relatively easily generate a bunch of valid equations to drive the task forward. And then it's relatively easy to evaluate whether each intermediate equation is good. So really, what is the thought? It's a problem-specific trade-off design for different problems. And the key idea of tree of thought is that if we design the thought space right, then we can use LLMs to systematically generate and evaluate thoughts and search in this space of thought. So what we did for this game 24 is that it's kind of like a thought level breadth search process or beam search process, where we use a very simple generation prompt to come up with a bunch of different equations. And then we use an evaluation prompt to assign a score to each of the possible equations. And then we keep only the most promising thoughts, and then we search again. So obviously, this evaluation prompt cannot be perfect, and it doesn't have to be perfect, just like any search heuristics. It just has to be good enough to bias the search into promising directions. And what we find is that the chain of thought approach can only solve 4% of the tasks with GPT-4, but having this systematic search process can significantly improve performance. So in this paper of tree of thoughts, we actually tried a wide range of different tasks, not just this kind of toy search task like in 24, but also tasks involving natural language like crosswords or creative writing. And we find that across various tasks with various features, we can actually flexibly define the space of thought and have this modular mechanism to generate thought, evaluate thought, and search thoughts. And it leads to a consistent performance gain across various domains. So it has become one of the most popular, widely used language agent method, and it has enabled a bunch of different follow-up applications where you can not just evaluate tasks, but you can also try to simulate humans or simulate other agents, or even simulate yourself and try to tackle some of the more practical tasks like jailbreaking of the language model or recommendation for products or auction games. So to quickly summarize this part, I think the fundamental essence of language agents is that we can think of reasoning as an internal action for agents. So what we actually show is that reasoning and acting can be complementary, and they can help each other to solve various tasks. And what tree of thought show is that if we think of reasoning as action, then some of the classical approaches to plan action, such as tree search, can be readily applied to improve reasoning. So language agents address some of the key limitations of language models and traditional agents because it's grounding language models with external feedback, internal control, and enables its future generalization to act in totally new domains, unlike traditional agents. So in the last part of my talk, I want to shift from those empirical tasks and methods and try to have a more overarching conceptual framework of everything we've discussed so far. So the motivation for a conceptual work instead of an empirical one is that we have already too many of the empirical works, right? So starting from language model, people have tried various ways to use the model through prompt engineering, and we have come up with mechanisms for reasoning and acting. But suddenly there has been, hundreds of papers now flowing on Twitter and archive every day, and various concepts and various mechanisms to use those LLMs to build various systems to solve various tasks. And this field is growing very fast, and it's becoming very overwhelming. But I think underlying all those empirical work, some of the fundamental conceptual questions haven't been answered, right? So how do we even make sense of the various LLM systems? How do we understand them, even they're defining very different terms and concepts and grounded in very different tasks? And where should the field be going, right? So if we cannot give a great conceptual understanding, it's very hard to make sense of where we should do next. So I want to draw a parallel to 100 years ago, where I think there's a similar situation for digital circuits, where in 1920s, 1930s, we have developed various analog and digital circuits for telegraphy, for various sorts of calculation of equation or stuff like that. But it has become overwhelming, right? So like underlying all those digital circuits, what is the principle? How do we understand them? And where should these circuits be going? Right? So something like von Neumann architecture actually gave a very good characterization of the circuits. And under von Neumann architecture, it becomes very clear what is the computational essence of the circuits and where should the field be going. And the field goes to this direction of general purpose computing circuits, which we call computers now. So I think we also need an overarching framework for agents. And that could be a guiding principle towards general purpose autonomous agents. And we do that actually not from scratch, but through some of the classical insights. So we draw from this concept of production system and cognitive architecture from Coxide and symbolic AI. So a production system is essentially just a set of rules where you have a condition and you have action. And if the symbolic condition is met, then action is triggered. So what I show here is essentially a production system for air conditioner. And you can argue that's possibly one of the simplest AI agents you can build conceptually. So the reason that I brought up this kind of alien concept of production system is that this has actually been the basis of symbolic AI agents 7 decades ago. And actually, the evolution of symbolic AI agents has, I think, gone through a similar process where things become more and more complicated to solve more and more complicated tasks. But around the 1980s, cognitive scientists and artificial intelligence pioneers like Noel, researchers proposed cognitive architectures as a framework to modularize and build complex symbolic AI agents using cognitive inspirations. So it has been guiding the development of symbolic AI agents. So how does this relate to today's language agents? I think the key insight is that we can really just think of language model as a huge stochastic production system, where you have much more knowledge than any of the production system we have ever built manually, but also it's stochastic. So once we draw this analog between language model and production system, it becomes immediate that those cognitive architectures can guide the development of language agents. So we propose this framework of cognitive architectures for language agents, which is drawn for Koala. And I think on a very high level, it's trying to categorize agents using 3 concepts. So the first concept is this concept of memory. So usually empirically, we don't think of memory. We just think of the context window of the language model and how we manipulate the string in the context window. However, empirically now we see that complicated tasks like sweepage, right? Essentially, you cannot possibly store all the information in the context window. There has to be a way to manage your context. And also, you want a way to learn from the previous experience and use the information in this task to help your future tasks. So I think the conceptual characterization is that you can really think of where agents store information as memory devices, where you have a short-term working memory that's roughly the context window of the language model right now. But you can also have various long-term memories, right? So we can think of the language model's weights as a type of precision memory, and we can update that kind of memory through gradient descent. But empirically, we have seen some new ways of learning where you can add task trajectories to an episodic memory and then retrieve it later for better task performance. You can reflect or get and infer knowledge and then add that to some data store, and then that can be retrieved later to help task performance. And even you can update the code of the agent itself and that can be also a way to improve the task performance. So I think all of that can be categorized into this second concept of action space. So action space, like I said, is a trivial concept for traditional agents because it's defined by the environment. But because we have those internal memories now for language agents, we can have systematic reasoning actions to update the short-term memory, and then we can have systematic retrieval and learning actions to read and write long-term memory. And then finally, we have those grounding actions to interact with the external environment, which is similar to the traditional agents. And lastly, once you have a space of actions, how do you make a decision? That goes to this concept of decision-making procedure, which is about how do you use reasoning and retrieval to choose an action. So on a very high level, what we're trying to do is we're trying to characterize each of the agent using only three concepts: memory, action, and decision. Well, how is that useful? So one of the usefulness of this framework is that we surveyed hundreds of papers, and those different methods, they work on very different tasks where using very different concepts. But through the lens of Koala, it becomes immediately clear what is the compositional essence methods, and we can immediately compare different agents across different tasks, understand the trend of this whole field, right? So one thing we can see is that we have made a lot of progress toward grounding those agents in various environments, robots, web, code, games, so on and so forth. But this concept of long-term memory is only getting started, where only recent work has started to explore how to learn beyond gradient descent, where we can write various pieces of information into a language store and then retrieve it later for task performance. And this concept of decision making is also only getting started. So tree of thought is some of the earliest work that's trying to go beyond just generating action, but instead trying to generate multiple actions and then evaluate each one or even simulate their consequences internally. So I think there will be a lot of exciting future directions in terms of long-term memory and decision making, and that seems to be where the field is going. So so far I've talked to you about a bunch of work around the central topic of language agents, and I think the way that they connect to each other is that first we propose those benchmarks, and those benchmarks have new challenges that motivate new tasks, and by summarize over all those benchmarks and methods, we have a conceptual framework, and this framework can actually inspire better methods and tasks in the future. So I've also worked on a bunch of different topics in my undergrad and PhD, and I think this framework of language agents, along with similar inspirations, inspire some of my future work. So due to time limits, I'll just talk about maybe two, I think, exciting directions for language agents. I think one is that I think training models for agents will be a very exciting direction, because so far what we see is that somebody trained the model for some purpose, and then we use it for various agent tasks, right? So GPT-3, GPT-4, they're not trained to be agents. They're trained to solve questions or dialogue. But what we see recently is that this recent work of FireAct, we show that actually if you can collect a bunch of this kind of language agent trajectories, they can fine-tune the model, and you can use a very small open source model to outperform large proprietary models. I think it's very important to establish this model agent synergy, similar to how GPUs and deep learning methods co-evolve with each other. So because GPU, they're not invented for deep learning, they're invented for playing games. And then we discover they can be used for deep learning. And then essentially those deep learning methods in turn inspired the future design of the GPUs, and they co-evolve together. So language models, they're not really trained to be agents, right? They're trained to generate tasks. But then we happen to find all those amazing usages of the models. But I think now is the time those amazing usages can inspire new insights and new data to train open source models, and they can perhaps provide the next trillion tokens for model learning, given that internet data is running out. I think another very exciting direction that I'm personally very excited about is how can we go beyond just imitating existing human knowledge, but instead discover new knowledge and even teach human knowledge in turn. So I think language agents have the potential to be the best professor, in the sense that they can personalize to each student and adapt to each student and give very personalized education. And they have this broad set of knowledge. It also has the potential to be the best PhD student in the world, because it could not only read, hundreds of papers every year, it could read millions of papers every day. And I'm sure there's a lot of ideas and concepts and inspirations if you can just combine, two random areas, and then you just find this idea. I think there's a lot of hidden ideas, even if we can just read more papers. Through the lens of koala, I think today's agents are not ready for them yet, because if you think about personalized education, it really requires a flexible long-term memory that's storing all the interaction with the student and trying to personalize according to that, because you don't want to fine-tune a model for each of the students. And through lens koala, you can see that for scientific discovery, actually one of the bottleneck is decision making. So, like as a PhD student, what we do research, what we do is extremely open-ended. So we have to rely on intrinsic motivation like curiosity. How to incorporate those kind of mechanisms into decision-making of language agent, I think that's one of the most important problems. I think it's a good time to stop and go to the actually important part of the talk, which is acknowledgement. So first, I want to thank my committee, and I want to thank Benchis for recruiting all the great students, and they have become my great friends. And even though I haven't worked with Benchi personally, but by interacting with her great students, I think I learned a lot. I want to thank Tom for all the classical insights. I have been wanting to work with Tom even before I entered grad school, and I'm very fortunate to finally work with him toward the end of my PhD. And I think it's been extremely helpful to learn POCSI, and I hope all this inspiration can help us to build better agents one day. I want to thank Sanjeev for the retreat, which has been clearing my mind this week, and for the retreat, which is promoting my thesis. So Sanjeev said in Twitter, this is a great thesis. And this has been a great compliment for me. So in my undergrad, I read his TCS textbook, and he's like a CS hero for me. And it's hard to imagine when he retreat and say my thesis is great. I want to thank Ben for making me feel old. It's surprising to find that my examiner is only maybe 2 years older than me. That's when I know I'm too old. I need to graduate. I want to also thank Tatsu, which is I think in Zoom right now, remote watching the talk. Thanks for shaping my talk. I think he actually gave me one of the best advices for giving talk. And even though I'm not his student, he shared all his job talk experience with me. I really appreciate that. So next, I want to thank my advisor and my friends. Karthik already gave a spoiler alert, how we meet, how this story happens. So I'll probably just skip that. I think it's a shame that, for all of my committee, I have no picture with him, so I will definitely take a picture with him afterwards. And then yesterday, I'll try to find in my picture with Karthik. And it turns out we only have, 2 or 3 pictures taken together. But I actually found a great one that we're together. Where you're my ring holder at my wedding. So it's like paper. You don't need a lot of papers. You just need high quality good ones. A few of them. Yeah. I think Karthik has not just been the best advisor for me. I feel like this photo illustrates. It has also been, I feel like, a best friend, a best big brother, and also like a best man. So I really appreciate the free environment that you give us and all the support, and it has been a great 5 years. And but in contrast to professors, I actually have a lot of picture with students, but I'm a man of simplicity, so I'll just put one picture here as a representation, right? So this is also taken on my wedding day, where all of the Princeton friends, they come to my wedding and we take this picture together. I think that's probably one of my happiest days in my life. And I really appreciate, Princeton, and I think not just all the great professors, but also I think all the great students that has been my friend. They have diverse interests. They are very friendly. They have been not just my lab mates or peer students, but also my lifelong friends. I really appreciate this support and this great atmosphere that Princeton has provided. And lastly, I want to thank all my collaborators and maybe take some questions. Yeah. Yeah.
One question about thoughts.
Yeah.
I remember correctly, the whole framework was guided through prompting and kind of control tools. So what do you think about the direction of teaching the model to do it by itself? Meaning, instead of having the value estimator or like prompt to generate thought, the model acting as an agent and then reflecting on its own actions while it acts, and then maybe instead of backtracking by deleting steps, just allocating attention to its past actions.
Yeah, so I think there has been some follow-up work where people essentially combine React and tree of thought, and the idea is you can not only search in the space of thought, you can actually search in the space of thought and action. So, for example, if you're trying to solve a really hard question, you can actually try to open various web browser tabs and not only make decisions over what you think, but also what you do in what web page. But I think there is a trade-off between how big your action space is and how hard your decision making is. So obviously, if you have a bigger action space, that means you're capable of doing more things. But that also means choosing over the actions, the decision making is harder. And I think one of the key bottleneck for this kind of combining tree search and language model is that language model is not very good at self-evaluation yet. And that's exactly why we need to train models for agents, like having this synergy. And
this follow-up work was also guided with like prompting and control flows, or did they actually teach the model to do it by itself, like in a kind of reinforcement learning framework?
Yeah, I think empirically what people tried is that you can try to generate a bunch of different trajectories, and then you can select the good parts, and then you can fine-tune the model on top of it. You can think of that as a very shallow or naive form of reinforcement learning, or where you're only using the good data to do imitation learning. I think that has been a very promising direction to improve, where the model isn't good at in terms of being an agent, right? Evaluation and decision making, those things that are not trained as part of the language model. But maybe, once we discover those usages, we can in turn train better models to suit those usages. Oh. Let's see. Yeah. Is there any question online?
Yes, I do have a question.
Go ahead.
Okay, thanks. It's a really good talk, and I do have a question on like the framework part, because I think it's very good for you to put this into a really big picture, like for a large language model as part of the big picture. Like, what do you think about the bottleneck of that like structure there? Like just CPU, because the processing time speed is really fast, right? But so sometimes the bottleneck is the memory part. So what do you think about here? Thanks.
I think empirically, the bottleneck is in terms of like where the field is going. Like I said, I think there's this bottleneck of long-term memory. We haven't explored enough how we can have this flexible context management beyond just putting everything in the context of the language model. And I think there's this bottleneck of decision making. So like I answered in the last question, right? Decision making is extremely hard, especially when your action space is very large, and how to internally simulate all the possible scenarios and self-evaluate. I think that's still probably a bottleneck. Yeah.
Okay, thanks.
Yeah, Tianyu.
I have a high-level question.
Sure.
So, do you think we'll have like an end-to-end agent system one day? So this is like, there's an analogy to auto driving. So like the Tesla's newest FSD system, they changed like the hardware planning system to like a neural-based system.
Yeah.
And like, it's like very impressive, like they can even understand like when a pedestrian waves to the car, like the car will just pass, instead of just out there. But of course, like that action space is extremely small compared to language agents.
Yeah.
I just want to hear your thought on like this kind of like more complicated components system versus like end-to-end system.
Yeah, that's a great question. I have a non-answer at the last paragraph of the Koala paper, but I think the short answer is that we can always think of the agent as a neural network plus some code that uses neural network. But essentially, the more capable the neural network is, perhaps the less code or structure that we need to use the neural network. I think for Koala, what we are trying to propose is sort of like a minimum framework of what is the essential components that's wrapping around this big neural network. But obviously, as the neural network becomes more and more capable, I think empirically we will need to use less and less complex scaffolding. And that's why I think it's very important to stick to very simple but general methods like React. I think also perhaps this is a way to collect data to better distill into the neural network, in the sense that we perhaps need to first have those scaffolding around the neural network to discover what they're capable of doing, and then to generate scalable data. And then maybe those data can be in turn to better increase the capability of the model, and hopefully we can have less structure along the way. But I think beyond just the empirical goal of building AI and building useful system, I think this framework is also very interesting if you want to understand intelligence, like as a science, or if you think about cognitive science, where it provides an understanding of what is essential. So I think at the end of my paper, I imagine a scenario where maybe one day GPT-10 can simulate everything as a chain of thought, right? You can have long-term memory or decision making, all the complicated things just through next token prediction in this one context window with 100 million tokens. But even that, I think it will be interesting to modularize, what are the components of the neural network that's doing those different components, and compare that to human intelligence and serve as a way to establish an understanding of intelligence.
Great.
Is there more questions online? Or... Okay.
Yes, I have one question. Can I ask?
Sure.
Yeah, so what are your thoughts on continual learning of LLM agents or just LLMs?
Can you repeat the question?
What are your thoughts on continual learning in the form of LLM agents? By continual learning, I mean adapting to different domains or adapting to an evolution in the domain. Like the domain keeps changing with time. So what are your thoughts on that?
Yeah, I think as this picture shows, if you think about long-term memory and you think about learning as just writing to the long-term memory, essentially you have, I guess, two ways of learning, right? You can either learn by updating the neural network with gradient descent, or you can learn by adding more knowledge or information into the textual part of your memory. And I feel like they might serve complementary strengths, right? So for tasks where you can collect a lot of examples and there's like a repetitive pattern, then obviously gradient descent might be the better way to go. But imagine some more open-ended tasks, like doing PhD research, right? So it's like you only do it once, and you learn along the way. And at least for me, as a PhD student, what I do is you learn all this knowledge, you learn all those experiments, and you learn all the skills, and somehow they're partly like a textual knowledge in my brain. So if I bring up the subject, I have this knowledge in my brain that I can retrieve and to help me. And for me as a human, like learning is this continuing experience where perhaps we're not just updating those muscle memory, but also those kind of high-level language memory. And I think that part is still not there yet for today's language agents. I think that's probably one of the most important directions.
Oh, thank you.
I have a question.
Okay.
Oh,
Go ahead.
oh, sorry. Okay, thanks. Great talk. There's a question in chat which I thought was pretty good, and so I'll kind of put that to you. And the question is, what do you see as the most likely way that language agents fail to maintain real-world traction in the coming years, or otherwise as not as significant as you anticipate? Maybe another way to think about it is like on this koala framework between memory, action space, and decision making. Like, what do you think is the bottleneck or the most challenging aspect of the framework?
I think your first question is asking about what are the domains in the near future that those agents might be most likely deployed. And the second question is, what's the bottleneck of the framework?
Yeah. And I guess they might go hand in hand because if it's if there's a big bottleneck, you would not see a real world application.
Yeah. I think my personal opinion is that maybe one of the biggest domain for application of this language agent is exactly the digital automation task that I propose. How to automate various tasks on the computer, on the internet, on those large-scale digital infrastructure that we have built and we work and entertain every day over. And the reason is that it's both scalable and practical. And obviously, there are also other applications like deploy this language agent ideas to robots or as chatbots, obviously. But I think in terms of the potential impact and the opportunity for improvement, I think we will see a lot of exciting applications for those computer using agents. And I think the bottleneck, as I said before, I think this idea of long-term memory and decision making, and that I think not only requires us to understand what's going on and what to do, but also I think a very important part is how to better train models once we understand what is lacking and what we should improve upon, which is how to better retrieve and learn and better make decisions by self-evaluating and self-simulating.
Awesome, thank you.
So let's say in a truly autonomous scenario, it's for human environment, and maybe safety critical. How do you think we can certify these systems such that we can be?
Yeah, I think safety is probably one of the most important topics for AI in general, but especially for those language agents, because if you think about the danger of a language model, right, it's mostly about generating hateful speech or biased verbal speech, but language agents safety concern can be much more because it could be connected to essential code or web or even robots, and once it has the ability to affect the real world, the safety concern is much more. I think for the safety problem, we first need a very good abstraction of what the agent even is. And I think the concept of memory, action space, and decision making can actually be important for safety purposes, because once we define modular memory devices, we can systematically define the write access and the access control for each of the memory. And maybe this user can only access this memory and this model can only access that memory. And only when we define a very clear action space, we can have some kind of estimation of the worst possible scenario and what could be the worst thing that could be done. That's the model actually, is the model actually able to change its own code, or is the agent actually able to control your whole computer, right? You need to first define action space and then estimate the consequence. And I think decision making is something interesting where if we can have a clearly defined decision making, maybe I guess the empirical way to go is more of a human loop approach where we incrementally build trust by interacting with the agents over long horizon. I don't think you want to have this fully autonomous agent deployed on your computer immediately and then do whatever they want without your permission, I think it might be a more gradual process where a trust is built incrementally.
Do you want to have a closed session or have lots of questions? Ask them. Yeah, that works. So in your, you talk about React and tree of thoughts, and those are sort of two extremes in the sense that React has one thought and then acts, and tree of thought has a lot of thoughts.
Yeah.
How do you think about how you should be thinking about how much model should be thinking?
That is a great question, and I think right now empirically, we don't have a good solution yet. So what happens is, for different tasks, you need to define, what is the right amount of thought, and what is the format of thought, and what is the proper length of thought, and to try to solve a given task. For example, for this question task, obviously, you don't need a lot of search, then the React format is good. And for those more search-oriented questions in task like M24, then obviously we design them to have more search and then more action. But I think if we want those agents to be more general purpose autonomous along the way, I think one critical issue is how it can make decisions over how much it wants to think about, and having it's sort of like a meta reasoning question. And I don't have a good solution yet, but I think drawing from human inspirations might be a way to go.
And then my other question is, in your first part of your talk, you focused on language as a domain in which we can evaluate these models.
Yeah.
And then you subsequently talked about reasoning. And I have a question about whether you think that there's something special about language that allows it to play both of these roles, right? So one role is it sort of allows you to define complex worlds, and this is something which allows us to evaluate these models in interesting ways. But when you're thinking about using language in the context of reasoning, it seems like that's something which is different from the way that you might think about other kinds of generative models or things that we trained, like a video model. When you video reasoning, I don't know, maybe you can video reasoning, right? But is there something special about language that allows it to play both of those kinds of roles?
Yeah. In my opinion, I think there are two things that are special about language that makes language agent different from the traditional agent. So language is a general purpose representation that we use to do various things. And that means first, language can be a very unifying representation to represent various domains. So we can make web navigation a text game. We can make a robotic manipulation a text game, and we can make dialogue a text game, and we can make video game also a text game. So I think this ability to represent various domains and various observations and actions, that's one part that's special about language. But I think language is not only a general purpose representation for representing those things. It's also a medium of thought and communication for humans, right? So so secondly, I think what's special about language is that you can actually have this mechanism of reasoning, which is kind of like self-communication that's in a way supporting a new way of generalization beyond just learning through lots of samples or manual rule design. And I think you can think of the manual rule design as reasoning in like a symbolic domain-specific language. And you can think of those neural agents, no matter imitation learning or reinforcement learning, as reasoning in a neural domain-specific language. But I think what's special about language is a predefined general purpose language, and we have our rich priors that we can operate over that, and that enables the generalization of language.
Again, talking about the React work, it seems like there's sort of two components. There's the reasoning on the length model, and there are these external calls to other sorts of APIs, be they calculators or knowledge bases.
Yes.
What do you think should be the relative cost of calling a knowledge base versus doing the reasoning? Like presumably the Google here isn't Gemini, it's Google's big knowledge base.
Yeah. You're asking what is the cost of taking actions, or what's the cost of doing the reasoning?
So OpenAI is paying two costs here. Or could be paying two costs. One is they're paying for you to use their server, and two, they're paying Google to get, or you're implicitly paying Google to query their knowledge base.
Yeah.
What are the ratios of those costs?
Uh,
What will they be in 3 years?
I think empirically, most of the cost is associated with the reasoning part, which is using language models API to generate all those language. Like usually the tool is relatively cheap. I remember, for example, this Google API, I think it's much cheaper than OpenAI API, the Google search engine. I think an interesting empirical question is that those language model API is designed in a stateless manner, meaning that if I generate all those thoughts and then those observations, if I do this locally, I can store those I can cache those keys and values and transformer states, and I don't have to recompute everything. But if I have a trajectory with 100 steps, that means I actually have to recalculate 100 times over the same pre-pending context. I think that's like a very interesting and important system problem that we need to solve. Maybe we need a stateful API.
You're allowed to ask questions too. I'll ask some more questions.
So you mentioned language is very special for reasoning. Is there any other type of reasoning that you think could not possibly be covered by language?
Yeah.
And language models like very complicated and basically a black box. We try to reason it with our way of thinking and to describe our findings using language, but what could possibly, is there anything that possibly exists that we can't really understand through language?
I think that's a great question, and the answer is yes. Obviously, language cannot reason over everything, and I think there is a need to incorporate multi-model capabilities into this framework of language agents. So I think you can think of recently there has been advances, I think, along two directions of multi-model. One direction is how to better turn images or videos, whatever, into language. Think of GPT-4V, for example. And there's, on the other hand, mechanisms to better turn language into other modalities. Think of DALL-E or Sora. I think it's important to think of how to incorporate those two types of mechanisms into this framework of language agents, because the first type can be seen as a type of multi-model reasoning. So if you want to work beyond the domain of language, you need to reason over images or whatever modality that the environment is given. And obviously, for example, for perception details, those things, like you obviously need some multi-model capabilities. I think what's interesting is that you can also think of things like DALL-E or Sora as a way to build better word modeling for decision making. So in Tree of Thoughts, for example, what you're simulating is just this language-based dynamics for games. But if you're trying to solve a more physical task, maybe you can think of DALL-E or Sora as implementing a way to build better internal simulation. And that can maybe enable better decision making, right? You can imagine if I kick the ball this way, how would the results look like? And then I can render the video and I can look at the video and see how good that is. And I think that could be a very interesting way to explore those multi-model models.
Earlier, you had mentioned that there might be differences in how much thinking would be best for like a reasoning agent. Could you ever imagine a scenario where like a React agent has another reasoning agent that helps it come up with how it should act, or like how do you think about having multiple agents to like enhance? Would that be beneficial, or would that be more fun?
Yeah, that is also a great question and a very important future direction that I didn't cover. So we actually have this follow-up work of React called Reflection, where the idea is, suppose the React agent makes some mistakes. but due to the nature of autoregression, it might be very hard for the real agent itself to correct its own mistakes because usually you don't have a lot of self-correction kind of data on the internet to train those language models, right? So what you can do is you can have an external critic or evaluator that checks the whole trajectory and gives some feedback. Say, okay, this is wrong, this is wrong, this is wrong. Maybe try this again, this is different approach. And it's shown to significantly increase the performance. I think multi-agent is a very interesting future direction, but my personal opinion is that we need to be careful how to define even a single agent. Because essentially, I think empirically, a lot of the so-called multi-agent methods are essentially just multi-prompt methods, where you have multiple prompts that's trying to do dialogue and try to solve tasks. But I think like if you think about humans agent, right, like the agent is more than just like a GPT-4 or whatever language model plus a system prompt, right? It has its own. Each of us have a long-term memory. We have our own like decision-making procedure. For example, like each agent should be much richer than just a language model and a prompt. So I think if the capability of each agent goes beyond a certain threshold, then it will be very interesting to see if we scale up the number of agents, how things will emerge. I think a parallel will be if you have a team of stupid people, then the more people you have, the less likely it's able to achieve the task. But if you have a room of smart people like now, the more people you have, probably the more likely you're able to solve more complex tasks. But I think today's single agent isn't really that good enough yet. So my personal opinion is we should make the single agent decent enough first, and then we can my personal opinion is we should make the single agent decent enough first, and then we can